Hello everyone, my name is Gabriel Muro and I am a researcher at Aberystwyth University. I'll be talking today about how we utilize high-resolution spectroscopy to probe the solar atmosphere. But first, I'd like to start off by thanking SPIE for inviting me to discuss our observations of the solar atmosphere, and also give special thanks to Hugh Morgan, the PI of the project and creator of this really cool background image of the corona, which is solar minimum on the left and solar maximum on the right. Also, thanks to Shadi Habal, the organizer of these difficult eclipse expeditions, as well as Adalbert Ding and Matt Gunn, who both made crucial contributions to the development and production of our spectrometer. Hugh, Matt, and myself are based in Aberystwyth University. If you haven't heard of it before, we're a small university in a corner of Wales with an active solar physics research group. Being that Wales only has two distinct weather patterns, cold and rainy, and very cold and very rainy, it's no surprise that we're all very, very fascinated by the sun and its mysteries. Okay, so we'll get started with a brief overview of the sun and the reason why it's an important topic. Then we'll briefly cover the current state of coronal observations. We'll get to the layout of our spectrometer, and how data was handled to get our Doppler shift measurement and also its significance. At the end, we'll go over planned adaptations to our device and how ground-based solar observations have a crucial role to play in our overall understanding of the sun. All right, so quick primer on the sun. While it is often a beautiful sight and makes life possible on Earth, it's also a difficult object to study since it burns our eyes and has a knack for oversaturating images. Just take this background image as an example. The first thing we notice is that there is essentially no detail of the sun itself, and lens flaring dominates the image. The key issue is that the excessive amount of visible light scatters in the Earth's atmosphere, which makes it nearly impossible to get any details about the optically thin solar atmosphere surrounding it. But a quick glance at the stat sheet makes the sun appear like a simple object. It's composed of nearly 3/4 hydrogen, 1/4 helium, and just a trace amount of what astronomers call metals. Now, in today's talk, I'll be focusing on iron. And to make it a bit more complicated, the surface temperature is 6,000 degrees Celsius, which is hot enough to vaporize every known element. So the iron that we'll be focusing on isn't the type of thing you cook with on the stove or lift weights with. Instead, it's iron in its gaseous and plasma phase. So where does all that heat come from? The major action takes place in the core, which is under such extreme pressure that hydrogen atoms will fuse together to form a helium atom. During thermonuclear fusion, a tiny amount of mass is converted into gamma ray energy via Einstein's famous equation, E = mc squared. And it's the same process used to create thermonuclear fusion on the Earth. So the sun's core is essentially releasing 100 billion thermonuclear bombs in its core worth of energy every single second. With all that energy, it's no surprise that the core temperature is hypothesized to be around 15 million degrees. But as we move outward from the core to the solar surface, temperatures drop significantly through the convective zone until it reaches a comfy 6,000 degrees at the surface. But calling it a surface isn't quite right. With such high temperatures involved, everything must be a gas or plasma. So the surface that I'm referring to is the outermost layer, which is optically thick, and which we call the photosphere. Here you go. So it might look solid at first, but it still flows like a fluid, unlike the surface here on Earth. It quickly becomes obvious that these fluid layers rotate at different rates. Once we crack open the sun, there we go, while also being conductive due to the high temperature and ionization. Thus, the solar dynamo model hypothesizes that there is a deep poloidal magnetic field, which is sheared differentially at the bottom of the convective zone. This creates a toroidal magnetic field that grows, distorts, and creates buoyant magnetic loops that rise and twist their way through the surface. This creates a wealth of chaotic magnetohydrodynamic activity at the surface in the form of sunspots, flares, and so on. That continues until the global magnetic field reverses every 11 years or so, and the process repeats. All of this leads to macroscopic magnetic events above the photosphere. like solar storms. So in the low corona, we see magnetic fields piercing through the surface and plasma aligning itself to strong magnetic active regions. Typically, these active regions produce most of the large-scale activity, although the exact process isn't fully worked out yet. But it's suggested that magnetic loops intersect and snap to release magnetic energy, such as solar flares. In order to conserve energy, this release is likely converted into a significant amount of heat energy as opposed to magnetic energy. While it's proposed that this flaring occurs constantly at nanoscale sizes all across the surface, it's only the largest of these flares which sometimes eject ionized particles off into space. It's clear in this flare in particular that it is ejecting material. Now, with the larger field of view of the corona extending out to many solar radii, we see what this plasma ejection looks like from a distance. So there you go. A large amount of plasma is fired off to the left. While this particular case is easy enough to spot, not all coronal mass ejections are associated with strong flares. This makes some CMEs a bit of a surprise, especially since they are hazardous to satellites and our electrical grid. So let's take a quick look at Earth's response to a CME. So plasma density is shown in color, and Earth is being bombarded by a shock of high-density reddish regions of plasma. In addition, strong lines of magnetic flux are compressing the Earth's magnetic field on the sunward side, which reduces our protective barrier against charged particles. In this instance, it's an animation of a typical strong CME impact on the Earth, one which was well measured back in 2006. But we do know from historical data that the Sun was capable of much stronger CMEs, such as the Carrington event of 1859, which obliterated Earth's magnetic field and induced current on the ground. The problem with CMEs is that we have no a priori predictive capability. So those that are associated with strong flares at least give us a chance to warn satellite and electrical grid operators, although the warning may not come at enough time. To make it worse, some CMEs aren't associated with flares at all. They're so-called stealth CMEs with a currently unknown mechanism driving them. Whenever the case, CMEs are capable of massive infrastructural and economic damage, so we need to understand the underlying physics of the corona to protect ourselves against them. And this is why I'm so interested in this enigmatic part of the solar atmosphere. It extends many solar radii until it becomes the less structured solar wind and appears to be magnetically driven plasma. The easiest features to study are the large coronal loops indicative of active regions, where density and brightness are large enough to easily track activity. What's less easy to see are streamers, which are also loops, but have been stretched out by outflowing plasma, but still maintain reasonably high density. Plumes are a bit tougher to see, as they are open field lines with plasma flowing freely out of coronal holes oriented around the global magnetic poles. But really, all of these features are pretty difficult to observe, often requiring a total solar eclipse or being performed in space. So let's take a quick look at the current state of coronal observations. The photosphere is covered by a wealth of space telescopes, providing excellent visible light imagers and a large set of ultraviolet spectrometers. Visible light spectrometers are rare, since separating any potential spectral lines from the bright solar disk is a huge technical challenge. Just above the photosphere, the layer known as the chromosphere, very thin, also has good visible light imagers and UV spectrometers up to around 1.1 solar radii. There's perhaps a bit of the lowest portion of the corona covered here as well. Then you've got this gap, which extends from 1.1 to about 2.2 solar radii, which is the low corona. Unfortunately, this region only has reduced quality visible light imagers, some of which are decades old, and no spectrometers in any wavelength to my knowledge. Thus, it is only available for spectroscopic observations during total solar eclipses. And above 2.2 solar radii, the picture gets much clearer again, with excellent imagers, UV, and infrared spectrometers. We've even got the upcoming Parker Solar Probe, which will dive down to 8 solar radii to get in situ data from the outer corona. Super cool stuff. But if I look at upcoming missions, things start to look a bit better for the low corona. First, we have the Solar Orbiter, which has excellent imagers, spectrometers, and a coronagraph to simulate eclipses whenever it likes. It's really an awesome spacecraft. And it's currently performing orbital adjustments to sync up with the Parker Solar Probe during one of its dives. But Solar Orbiter itself is going to stay at a safe distance and thus only get down to about 1.7 solar radii with its suite of optics. Next, we have Proba 3, which will have its Aspix coronagraph in tandem orbit. It will be much more ambitious in regards to observing the corona. Its white light imager and helium tomb polarizer will make observations all the way down to 1.8 solar radii. So in some ways, we'll finally have continuous white light coverage when combined with other spacecraft, and at least one diagnostic from tens to hundreds of thousands of degrees. Except that Proba 3 has so far been delayed 3 times now, currently until 2022, and it won't be in operation for a while. But even when Proba 3 is launched, it still leaves observations of the low corona region up to about 1.7 solar radii still a bit lacking. We won't have any spectrometers for this critical region of space weather studies. The reason why this layer of the atmosphere is so important ties back to some of the earliest spectroscopic observations, which coincidentally happened during solar eclipses. Way back in 1869, an unidentified green line, this one right up here, was discovered during an eclipse. Now, at the time, 530 nanometers didn't correlate to any known element, and it was thus dubbed coronium, as some new exotic atom found only in the atmosphere of the sun. But if we fast forward about 70 years, Grotrian and Edlin made a suggestion that the green line wasn't a new atom at all, but instead a simple iron atom ionized to just ridiculous levels. They suggested that neutral iron atoms could emit at this wavelength if they were heated to 2 million degrees Celsius, in which case they would lose half of their 26 electrons. So this seemed a little absurd at the time, since the photosphere was only 6,000 degrees and the chromosphere above it was just a few thousand degrees higher. Yet somehow the corona was 3 orders of magnitude warmer at just a fraction of the solar radii above it. And since then, we've confirmed again and again and again that the low corona has consistently sustained temperatures of 1 up to 3 million degrees, regardless of any obvious solar activity below. Which is weird, because after all, when you move away from the heat source, temperatures usually go down, right? They don't skyrocket up by 3 orders of magnitude. So at present, we have no clear idea of why the corona is able to sustain this temperature. The most popular suggestions are forms of alphanic wave heating, magnetic reconnection, or flare warming, all of which have issues when we compare simulations to observations. Thus, the corona is an observational missing link down here below, or in the 1 to 2 solar radii region. Since this is where the solar wind is heated and accelerated and where coronal mass ejections form. Thus, we at Aberystwyth University here have built a high-resolution spectrometer to generate diagnostics for this region. So our portable spectrometer is a 3-channel visible and near-infrared device centered on 3 iron emission lines designed to fit in a carry-on piece of luggage. It's still heavy though. For the 2017 and 2019 eclipses, we let the sun track across the sky on its own, allowing for our spectrometer slit to do pretty stable scanning at a rate of 1 solar radii per minute. The last 2 solar eclipses lasted around 2 minutes each, so we were roughly able to cover the region outlined on blue over here on the right. and capture 3 wavelengths simultaneously in the process. The optics of the spectrometer was designed by our good friend Adalbert Ding, funded by the STFC, and built in-house by Matt Gunn, our resident optics specialist. And I am very, very, very thankful for these guys. This thing so far has been rock solid and thankfully tough to break. The reason we chose these 3 iron ions is because they represent about 1,000,000 degrees of temperature range. And if we take a look at narrowband spectra from the 2010 eclipse, we see how temperature-dependent features can be. Take a look at the upper left here, which only has a hint of a faint streamer. Yet, in the wavelength associated with temperatures 1,000,000 degrees warmer over here on the right, we see that that same upper left portion shines brightly as a streamer. So coronal features like this display the significance of various degrees of iron ionization equilibriums. And let's take a look at the build of our spectrometer. Unfortunately, the 2017 device had some issues and data was deemed unreliable, but this year's model worked out quite well. First, we have a large objective lens to gather light, then reflected into a white light slit jaw camera for context images. The rest of the light passes through the slit and goes through a series of dichroic mirrors. Each mirror acts as a beam splitter and a bandpass filter to only let the relevant wavelength reach the diffraction gratings. Each grating is set to a very high order, giving us a small spectral range of just 15 to 19 nanometers across a full spectral image. The sample resolution is very high as a result, as low as 0.011 nanometers per pixel. And we've got around 1,400 pixels to work with. This allows us to measure that critical 1 to 3 solar radii region with great diagnostic capability. So with our compact spectrometer, we and the rest of our SolarWinds Sherpa team headed out to Rodeo, Argentina to test our device during the 2019 solar eclipse. Our site was around 1,700 meters high in elevation with cold and very dry conditions. Basically, really good conditions for the spectrometer, but terrible conditions for the human operators. And to make things a bit more challenging, I found out at the last moment that we would need to manually track the sun, which is what Steve is doing. So it was a bit of an extra effort, but still worth it to see this. Now, if you look closely, you'll see all us little yellow SolarWinds Sherpas running around on the left side and the right side of the building. Thankfully, we didn't have a cloud in the sky that day, and it all turned out wonderfully. You could probably tell by that big smile on my face if you caught it quickly. Let's see it one more time. All right, look how happy I am. Okay, so let's go ahead and get to sorting out the data from this eclipse. So with the large field of view from one of the photographers in our group, I spotted a notch in the so-called diamond ring phase of the eclipse. This was really helpful for orienting the spectrometer's slightly off-centered manual tracking. So here's the sun's path and the spectrometer path that I was able to figure out. Then, with an even wider field of view of the eclipse with a beautifully processed white light image from Chile, that occurred about a minute earlier. There you go. I combined the full spectrometer field of view in the gray box and highlighted the portion with useful spectrometer data in the smaller blue box. Because this was my first time using the device, I wasn't quite sure about exposure timings, but 2 solar radii by 5 solar radii is plenty to work with for at least our purpose today. And before I really get into this, I just wanted to show you guys what a quick shot of what spectrometer data looks like before cleaning it up. Doesn't look like much, right? Okay. So first thing we need to do is identify wavelengths of interest. So we had to figure out where this iron ion wavelength is hidden. I tried at first using laser calibration, but as you can see in the green and blue lines here, it varies kind of a bit based on ambient temperature. And Argentina was very, very cold, while Wales wasn't, well, it wasn't warm, but it wasn't nearly that cold either. So I switched to using traditional calibration lamps instead, namely neon and krypton. And taking a quick look at one of the images from very close to the sun on the left, and then moving further and further away as we scan to the right, we see this iron 10 emission is getting weaker and dropping down closer to the blackbody curve, as should be expected. Next, I created a flat field background in our optics lab to get a clear idea of each channel's response. What's graphed here on the bottom is a one-line sample across the channels. It may look a bit uneven, but we're only focusing on the 30-ish pixels centered on our wavelengths of interest, not the full 1400 pixels all the way across. So not such a big deal. Also, if your eyes are sharp, you might notice a slight curve in the 637 channels image, right there-ish. But I'll deal with that in a moment. Then we rebalanced each channel's brightness to match what the integrating sphere was outputting. The camera response and the dichroic mirrors shown on the left really offset the brightness of each spectrum. I used the iron 11 as the baseline since it had the worst signal-to-noise ratio, and then adjusted the others to match the expected blackbody curve of the sun. That way they're just all normalized brightness-wise. Also, remove the dark frames as well. Once the spectral lines were all balanced and popping out nicely, the next step was to fix this optical effect, which is known as a smile. Really curved, funny looking thing there. So I first wrote a code that automatically mapped the circular feature, which you can see in the cyan and magenta there. We'll focus on the cyan. Then I had my code solve for the circle center, which is way off of the image onto the left. Next, the code straightened out the image on the vertical emission line we were aiming for, and this made integrating far easier to code and also preserve signal at the top and the bottom of each image. It also fixed a small amount of tilt due to tiny misalignments inside the spectrometer. So that's cool. And after all this processing, I then attempted to fit a Gaussian function line by line, as you can see this little green line moving down that narrow portion of the image with the iron emission that I was looking for. By establishing this requirement, we were able to do real spectral diagnostics with the data, specifically in this case, determining not only that a reasonable Gauss fit exists, but also where the center of the spectral emission is. So here's an example Gaussian from the green channel that follows the function wonderfully, at least on one of these lines here. And next we have a white light image showing the full magnetic structure during the eclipse by Milos Druckmeiler. Really beautiful stuff, but you might notice that the image is tilted due to our manual tracking being a bit off. Okay, and finally, the area here where the emission lines do and do not pass the Gauss fit test. The map spots are where the Gauss fit was successful, and that's what we're working with next. But I realized that my initial Gaussian test was a little too forgiving. Some of these Gauss fits were essentially just one slightly bright pixel, which you can see just right there. That hardly qualified as an emission line and resulted in far too many false positives, as you can tell. So I cleaned it up a bit more to get rid of these, and we're left with only good Gaussian-loving spectral emission lines to work with. So let's see how much neater this all looks. Ooh, nice. All right, so we're done with this data reduction. Let's take a look at the big preliminary result that I got. What we have here is Doppler shift, measured via the basic Doppler velocity equation listed over here on the upper right. Our device has both a baseline wavelength for each iron ion, noted by lambda naught on the denominator, and the measured wavelength in delta lambda on the numerator. So we take the ratio of those, multiply it by the speed of light, and we get pretty confident measurements of how quickly these ions are moving towards us. This is why I went through all the effort of making sure those Gaussians were good, because being off by just half a pixel can lead to a 2 kilometer per second difference when considering the rotation rate of the corona. So let's focus on the green channel over here on the left for now. It looks like it's mostly around 6 kilometers per second overall, with some bits moving a little bit quicker and perhaps a little slower as you move away from the center. Now let's compare it to recent rotation rate estimates by Lee et al. The bulk of the corona is moving fast towards us, but there are areas moving even faster towards the top and bottom. It's still within the realm of reason because they were integrating the average rotation rate over several months to years, whereas what you're seeing now are some of the highest precision, near instantaneous coronal rotation rates ever measured. Cool, huh? So what does that mean? The big implication for this, assuming I didn't make some major mistakes along the way, is that the corona is rotating independently of the photosphere. While we normally measure equatorial rotation, that being the latitude under this big streamer on the right, so equator, essentially, to be the fastest region of rotation. That only seems to be the case in the photosphere, though. With these coronal measurements, it's the opposite. The plumes, which lie above the high latitude polar regions, seems to be rotating faster. See for yourself. And overall, the base of the corona seems to be rotating faster than the photosphere overall as well. How is that? Is it driven by nanoscale magnetics? Does coronal rotation vary? That's been suggested but not clearly observed on short timescales. Unfortunately, while this is a tantalizing clue, it's not the full picture that I'm hoping for. The area of the corona that we measured lacks any loops or prominences, which might have photospheric footprints tied closely to them. So it's unclear if perhaps the dynamics of this large streamer over here has done a bit of trickery. But thankfully, this year's total solar eclipse is coming up and will provide an opportunity to measure the full corona this time. Hopefully with loops, prominences, streamers, flares, coronal mass ejections, the whole bit. So, future work. For now, I'm writing up the results you've just seen in more detail and developing a temperature map with some inferences about the iron ion abundances as well. In our upcoming eclipse, which I really hope is going to happen, please, Argentinian government, let us be essential. We'll have some minor improvements to our device, namely with automated tracking this time. We'll be able to pan across several solar radii to increase the overall scale of our spectra. And the context imager will cover a wider area as well. And most importantly, to me at least, it will be a bit lighter, so it won't hurt my back as much to carry it around across the world. Now, unfortunately, due to delays relating to the situation affecting all of us across the world, some of our most significant design plans needed to wait until following eclipses. But let's take a look at what some of those are. So the first major enhancement is the addition of a fourth channel that measured in infrared, centered at 1079 nanometers. There needs to be some spectral range around it, because the idea is that we'll be pretty close, or we'll be able to close that temperature gap between 1 and 2 million degrees by measuring iron-13. And we'll also be able to look at cool neutral helium, which gives some unique information about where ion recombination dynamics are occurring within the corona. Next, we'll be aiming for a high-resolution hyperspectral imager, which will record broadband spectra in detail. I'll talk about this more in a moment. Finally on the wish list, probably more than a couple of years out at this point, is a ground-based coronagraph. With this additional component, we'll be able to reproduce solar eclipse conditions at will at high elevation sites. This is a challenge due to atmospheric scattering, but the PI of our project, Hugh Morgan, is pretty confident that an occulter and optical design can be refined and built based on experimental data. Either that or we toss it on a space telescope. Who knows? I really don't know much about this coronagraph plan, but if you're interested, shoot me an email and I'll pass it along to Hugh. Okay, so back to the hyperspectral imager, which should be ready in time for the 2023 or 2024 eclipses. What we plan on doing is replacing our basic white light context camera with a high-resolution imager that measures a variety of broadband spectra with very, very rapid scans. An example image is shown on the upper right, where a variable filter has been placed on a typical DSLR camera. We can clearly see that the red filter is much more dispersed compared to the green and the yellow. And by using several filters, we'll be aiming to get a full broadband spectrum for every available pixel during the eclipse. This hyperspectral data cube, as it's called, on the bottom right here, shows reflectance and dispersion of the entire image at every available wavelength. So this is a pretty advanced addition to our device, and we are a small university off in a corner of Wales, but we are pretty lucky to have plenty of optical expertise within a department, as the ExoMars PanCam hyperspectral imager was built here. And you probably heard all about that in the previous talk by Andrew Coates. So it was co-investigated and manufactured right here in Aberystwyth. So our coronal science measurements can really benefit from a hyperspectral imager. With a high-resolution broadband spectrum at each pixel, we'll gain insight into the other major component of coronal plasmas, the electrons, not just the ions. By taking a look at the figure on the right, you'll see that the K coronal model spectra displays a solid black line indicative of just 500,000 degrees electron temperature. Note how well defined the peaks and the valleys are for that solid black line in comparison to the dashed lines at higher electron temperatures. This is because as electron temperature rises, so does the bulk electron velocity move in all directions. Thus, you smooth out the spectrum as temperature and bulk electron velocity rises in a very distinct temperature-dependent way. Combined with the device we already have, and the fourth channel, which we'll be building next, this single device will be able to create exceptionally robust snapshots of coronal dynamics during eclipses. And the best part is that it should still qualify as an airplane carry-on, because there's no way in the world I'm checking this thing into regular baggage. Oh no. Alright, so in closing, I hope I established early on that we need to realize that there's more than one corona threat to be concerned about. While these massive solar storms might only happen once every 100, 200, or 1,000 years, they do indeed happen. And we need to be prepared, because if an entire continent, or two continents, lose their electrical grid for months or years, then we'll be thinking back with very fond memories of how great and lovely the year 2020 was. Additionally, the corona appears to be decoupled, and due to the plasma nature of the iron ions that we measured, we can at least say that the reason for this is magnetic in nature. It may not mean too much on its own, but as a part of the bigger coronal heating puzzle, it could be a key piece of information. And of course, ground-based solar observations are alive and well. They do not need to be excessively expensive. While it is wonderful that we've made such great progress with major spacecraft and ground-based observatories, there's still an important role for us small ground observers to play as testing grounds for future missions and concepts. Finally, eclipse spectroscopy currently fills a very important gap in solar atmospheric observations, and will continue to do so, especially as portability and reliability play a key role in future instrument design. All right, so that's it for me. Thanks very much to SPIE for inviting me to speak. Thanks to Aberystwyth University, including Principal Investigator Hugh Morgan and my technician, Steve Fern, for providing the expertise and opportunity to take a leading role in this project. And thanks to Shadia Hibal and the Solar Wind Sherpa Expedition team for organizing these events in the past and even continuing to do so in the most difficult travel environment of our lives. We're all quite hopeful that we'll be able to do this again in December, maybe wearing full hazmat suits or something like that. Who knows? But finally, I'd like to thank you, the one sitting at home, staring at the screen, and been listening to me for half an hour. Yes, that's you. Thank you so very much for listening. So do you have any questions?